Good afternoon, students. Dr. D again. Here is our Chapter 4 video, and this gets into some advanced materials, so we're going to stick with mainly the earlier part of the chapter and some of the fundamental stuff as your outline dictates. And more of what you'll see on the quiz. We will get into Lewis dot symbols, but that'll be just the real beginning of the in-depth material. We're going to focus on just types of bonds, naming compounds and writing their formulas, and polyatomic ions. Get you on board with all of that stuff so that in class we can focus on spending time on more advanced things like Lewis structures. So there's in general three types of bonds. We're only going to spend time talking about two of them. I'll mention metallic bonds, and they're here, listed here. Basically, this is for your elemental metals, okay? So if we're thinking about copper here, iron, things like that, that's what you're dealing with, okay? Not compounds, not metals within compounds like iron chloride or something like that, just pure elemental metals. And they tend to have like these delocalized electron distribution. It's kind of like people describe it as like a sea of electrons. So the electrons are not held by any individual atoms fairly tightly. They kind of flow and exchange easily, and that's what makes them great conductors of electricity. With ionic bonds, the electrons are kind of transferred. They're transferred from, the species that doesn't like electrons very much to one that does like it more. And we think about electron affinity, ionization energies. Those type of things can help you understand which of those elements would like and dislike electrons. And clearly something like potassium chloride. Chlorine is going to like an electron, and potassium is not going to like an electron based on electron configurations, trying to get that valence shell filled, or losing an electron to have an outer shell filled. And that's going to be electron transfer, and then the opposite charges attract each other, and that's what builds the crystal, if you will. And remember what we talked about in the beginning of the semester. There's no such thing as like a sodium chloride molecule, okay? You can only get really small crystals. You're still going to have thousands of atoms there. And you can see if you take one in the middle, each chlorine, which is green here, is going to be surrounded, you can't see it, by 6 potassium. And each potassium will be surrounded by 6 chlorines. So here you see this potassium's going to be surrounded by 1, 2, 3, 4, 1 back in there, 5, but also 1 out here as the crystal keeps going. But this is the end of the crystal, so this one is not completely surrounded. And then you've got your covalent or molecular compounds. And this is just an element, homogeneous diatom here with bromine gas. But here the electrons are more shared. Okay, they're not always shared equally, and we'll talk about that a little bit later, but they are shared rather than transferred from one of the species to another. So what you wind up with is an electrostatic attraction. Opposite charges attract. You have that cation and anion, and this helps to achieve stability for the ions. And this is the reason why there isn't a single sodium chloride molecule, because that charge is not isolated, if you will, in the sense that, just attracting that sodium, just attracting one chlorine is going to stabilize it. It's going to kind of insulate that charge. So it'll be surrounded on all sides, and then each of those is surrounded on all sides. A covalent bond in covalent compounds is more of an equal sharing. And we talk about bond length and bond strength here. This is something that's discussed at the end of the chapter a little bit. But just measuring them, there's different ways in which these can be measured. In terms of ionic compounds and covalent compounds, that's something you're responsible for, and we'll talk about energy of the bonds, the strength of those bonds at the end of the chapter. As far as the ionic compounds, we can actually, calculate what's called this electrostatic potential energy. Now, we're not going to do this, and we're just going to look at it in a qualitative sense. And this is actual coulombic charges here, so you'd have to actually have that value, and this is the distance of separation. But all we're going to do is look at the fact that we're going to put in here, fictitiously, a way of looking at this. We're going to put in the actual charges. So if it was potassium and chloride, it'd be +1 and -1. You don't have to worry about the signs, actually. So it would just be 1, the charges. And if it was something like calcium oxide, it'd be 2 and 2. and you're not going to calculate anything. You're not going to use this constant. But what we're going to do is look at that relationship. As the charge increases, the energy increases. This is what we call this lattice energy, the strength of this crystal. So it should make sense to you. +2, -2 are going to be attracted to each other more than +1, -1, and therefore make for a stronger crystal, stronger attraction. And of course, the distance of separation, the greater the distance of separation, the weaker, because it's in the denominator, so they're inversely proportional. And what that means is, what's the distance between the ions? Well, we can estimate that by size. If you have two small ones, a small cation and a small anion, the distance is from the center of the nuclei, if we did use that as a way to estimate the distance. Then if you have a large cation and a really large anion, well, the distance of separation is greater. That's going to make the attraction weaker. Okay? Because remember, what's attracted here? The nucleus here attracts the electrons in this. The nucleus here attracts the electrons, the electrons here. Okay? And the nuclei repel each other, and the electrons in the opposite atoms repel each other. So there's multiple forces going on here. It's not so easy just to say, oh, yeah, well, +1, -1, the negative electron, extra electron of one is attracted to the nucleus of the other. No, there's multiple attractions going on here. But we can use this as a way to kind of simplify and get at the heart of things, and that is just put in the charges right here. 2 and 2. And once again, you don't need to put it into this formula. All I want you to do is understand that, a +2 -2 has a greater attraction than a +1 -1. And a +2 -1, so if you had calcium chloride, that would still have a greater attraction than a +1 -1. Okay? And the larger they are, the weaker the attraction because they're more apart from each other. So this is that lattice energy. And you can see it here. Look at magnesium oxide. And then with a +2 -2, the largest one on the chart, right? And then look at size. Chlorine is larger than fluorine. And they're both bound to lithium, and it's weaker. So this is the energy, if you will, that I would have to put in to break apart that crystal. All right, so as you get down further in the periodic table, they get larger, right? Comparing these three, and look at what's happening, right? The lattice energy is decreasing. So there's the size effect. And then you jump in and you see, okay, here's a +2. That jumps up. Here's a +2 -2. And that jumps up even more. I don't need to say anything more here. I think I said what a metallic bond is. And that's really all. You're not going to see any questions on that. It's maybe a quiz question with the bonding, but it's not something we're going to go into details on. Now, the covalent bond, you might guess that not all atoms like electrons the same, because you looked at electron affinity and ionization energy in the previous chapter, and you know that to be the case. So that means if I bring together two bromines, yeah, they're identical. That's a perfect covalent bond. But what if I bring together, a carbon and an oxygen? Does one of those like electrons more than the other? Yes. So you wind up what's called a polar covalent bond, as opposed to a nonpolar covalent bond, which would be Br2 would be. And it's a result of the unequal sharing of electrons in the bond. And you can think about it in terms of, the elements that like electrons, the ones with high electron affinity or low ionization energies, or high ionization energies, because they hang on to their electrons, so it takes a lot of energy to remove it. So that's what you would expect. We just need another term to describe how they behave within a bond, and that's the Pauling's electronegativity after Linus Pauling. And it gives you ideas of the electronegativity differences. Okay, it has to be 2 or greater, the electronegativity difference, to be considered truly ionic. And you see that with chlorine and sodium. 3 and 0.9 is 2.1, so it's just ionic, really. But some of these metals and nonmetals are not really considered ionic. If you look at chromium, it's 1.6. I combine chromium with chlorine, it's only a difference of 1.4. That would be considered a polar covalent bond, not an ionic bond. So you learn in high school, maybe a metal and a non-metal is an ionic bond. I'm here to tell you that's not really a good way of describing it. You want to look at electronegativity differences. And if it's considered 0.4 or less, that's close enough that we say it's kind of nonpolar covalent. So if you put together carbon and hydrogen, 2.1 and 2.5, that's 0.4. That's considered a nonpolar covalent bond. Now keep in mind, this is just terminology. Clearly, bonding carbon to hydrogen is more polar than bonding two carbons together or two hydrogens together. So it is just, humans' vain attempt to categorize everything. It's once again really a continuous spectrum of polarity, all the way from completely nonpolar covalent like Br2 to completely ionic, which would be like francium and fluorine. 0.7 and 4.0, now you got a 3.3 difference. That's a hugely ionic bond. And you have everything in between. Okay? So it's important to realize that. This is just a little bit of a terminology we use. So this is the electronegativity scale. And it's very simple. It increases up and over. Fluorine being the only element with a 4.0 value. And you can look at this. I think the real scale has 3 sig figs rather than 2 sig figs. And I think fluorine's actually 3.98. But anyway, 2 sig figs is fine. And you can see the trend. Oxygen's the next most electronegative element with nothing with a 3.5. And then chlorine and nitrogen are both 3.0. And then bromine's 2.8. And you got sulfur and carbon both 2.5. You notice hydrogen's kind of over here now. This is one of those schizophrenia things I told you about. It's really got an electronegativity. It's a non-metal also, so we like to see it over here, an electronegativity like that. But it forms a +1 charge, and we know that group 1 forms +1, so that's why it's over here. So you get that hint of that. So this is this idea. So HCl and NaCl and Cl. So equal electron distribution, no red there at all. Here we got a little orange showing up, showing electron rich, and here we got heavy rich red to show a strong electron distribution there. And these are somewhat drawn to size in the sense that this computer models chlorine is going to be bigger than sodium cation, chlorine bigger than the hydrogen here. So that's our electronegativity and polar covalent bonds. Now the naming, I'm going to ask you to do most of this on your own, otherwise this video will be really long and it'll be boring in class. Your book does a fine job. I will ask them naming questions both on the quiz and the exam to make sure you learn, but I'm not going to emphasize it. You'll learn with time, and as you become more familiar with the terminology and the nomenclature, you'll become more and more familiar with it. So I'm going to stick to the basic names. If you get the basics down, you're fine. Don't worry about a bunch of exceptions. I'll ask you maybe one name of an acid and one oxo anion that's common. Otherwise, I just want you to be able to name binary molecular compounds and ionic compounds. So the binary ones is where we use the prefix. The binary molecular ones is where we use the prefix. That means they're going to be nonmetals only. So this is where you get sulfur dioxide, okay? Dihydrogen oxygen, which is water, right? Carbon dioxide. These are all nonmetals, and you use the prefixes, okay? You never use mono for the first element. We just drop it. And sometimes we drop a value if they're two vowels together. Yeah, it's multiple choice. You're not going to have to worry about that, just so you realize it, though. And you just combine the two. That's all. So it becomes pretty straightforward. Carbon dioxide, dinitrogen pentoxide. Okay? That's where you would drop the A. Instead of say pentaoxide, you say pentoxide. To me, it's not a big deal. I don't know why they bothered to drop the A. Pentaoxide is not that big of a deal to say or a mouthful, but for some reason the A's, the vowels drop there. And we'll do some examples in class. I'm just not going to spend a lot of time explaining the rules to you. And in class, neither. So you come into class ready to just do some examples and help me to name compounds. Now, binary ionic compounds, you just use the first word of the cation, and then you add ID ending. And you all know this for sodium chloride. right? ID ending on the chlorine, and you just use the sodium cation. So it's sodium chloride. You don't have to use any numbers if it's a group 1 or group 2 metal, right? It's just calcium chloride. Everyone knows calcium's 2 plus and chloride's minus 1, so therefore we know that calcium chloride is CaCl2. But with transition metals, it varies because some of these elements have multiple charges. Copper is both 1 and 2, very commonly, copper 1 and copper 2. So if you say copper oxide, no one's going to know what that means. You have to say copper 1 oxide or copper 2 oxide. Copper 2 oxide is CuO because the copper and the oxygen cancel each other out, plus 2, minus 2. Copper 1 oxide, you need 2 coppers to cancel out that minus 2 oxygen because oxygen's minus 2. It's in group 6, 2 electrons away from that octet. An old naming system is cuprous and cupric. I'm not holding you responsible for that, making you aware of it if you see it, but I'm not going to use it on quizzes and exams. Polyatomic ions, these are just ones you have to start to memorize and become familiar with because you've got to be able to recognize them in chemical reactions, which is going to come up in Chapter 7. We're skipping Chapter 6, so after this exam of 4 and 5. And they'll be necessary to know them for naming. So some carbon ones common ones you'll see a lot is carbonate and either bicarbonate, hydrogen carbonate, the acetate ion. This is for acids you see that. You might see that in lab. Nitrate are real common. The ammonium cation, that's the only one that's a cation on this list. Sulfate and sulfite are real important. And the hydroxide ions. So start to get familiar with these so you can name them and recognize them in chemical reactions. The reason is because they don't fall apart in chemical reactions. And in chemical reactions, if I have something like, let's just say I've got sodium sulfate on the reactant side, and over here on the product side I have something else. Let's say I have, and it just reacts with something, it doesn't matter. And let's say I wind up with barium sulfate over here. What you got to realize is that sulfate stays together all the time. That's one of the keys to being able to predict products and reactants, recognizing these polyatomic ions. Permanganate's another one you'll see a little bit of. If we add hydrogens to these, they'll be acids, and you'll have, perchloric acid, chloric acid, right? Chlorous acid, and hypochlorous acid. You'll see that in your book as you get familiar with the naming of acids. So this is the idea. So if you have multiple oxygens, they name it in a sequence of up to 4. Not all of them have 4. So for example, sulfate and sulfite, those are the only 2 ions, polyatomic ions. So you only use the 8 and the ite. And the one with more is always going to be the 8. Okay? With nitrate and nitrite, same thing. Okay? And you can add hydrogens to those to make nitric acid and nitrous acid. The 8 becomes ic, the ite becomes us. And you'll see that in the acids. And then you've got just basic acids with like the hydrogen and the halogen, hydrobromic acid, hydrochloric acid. You've seen that one in lab probably, maybe not yet. But you'll see that. So get familiar with naming those. And here it is. Here are the acids. Okay? So that's just something I need you to do on your own, and we'll talk about it a little bit in class. The last thing I want to talk about in the video is this idea of Lewis theory after Gilbert Lewis. And his idea was to come up with some sort of accounting system for electrons and how they're shared and transferred in molecules and in crystals and things like that. So this gaining and losing of electrons. So we'll go into compounds and notating them, and I'll do a little bit here with ionic, but I really just want you to get familiar with the Lewis symbol. So basically, anything in group 1 is going to have the same exact dot notation because they all have one valence electron. That's all we care about is the valence electrons. Okay? We're not worried about the other electrons because they're core electrons that aren't important in bonding. So that means the only thing that changes in group 1 is the symbol. The only thing that changes in group 17 is the symbol, 7 valence electrons. So you notice what you do. Here's your symbol. You start by putting 1 and then 2. It doesn't matter which side. You don't pair them up until you have 1 on each side. That's where you see carbon, right, in group 14. Then you start pairing them up. And it doesn't matter which order you go in. People use conventions, but it really doesn't matter. Okay, and now what that's going to help you see, and we'll see this in a bit, is the number of lone electrons, unpaired electrons, is the bonding capacity of the atom. So you can see the carbon has the ability to bond in 4 places because it has this 4 lone electrons. Okay, that'll become more clear in chapter 5, which gets a little bit advanced, but you might be thinking to yourself, well, wait a second, 2s2, 2p2, there isn't 4 lone electrons. 2 are paired and 2 are lone. Hang on to that. That takes us into hybridization, molecular orbital theory, and all that. So just go by the group number now and the number of valence electrons as you move across. And then so we can see why sodium and chlorine make such a great pair now from this Lewis dot diagram. Sodium can easily get rid of 1 electron, and then it will have 10 like neon and have that noble configuration of neon, right? Chlorine will pick up 1 and have a noble dot configuration of argon. And you can see they make a great pair, right? One wants to get rid of 1 and one desperately wants to pick it up. So there you see it. Chlorine's going to add that electron. Sodium's going to get rid of that 1. They're both going to wind up with octets or noble gas configurations. And with that, that concludes the video.